Hi, and thanks for your interest in VDSM, a method for unsupervised video disentanglement with state-space modeling and deep mixtures of experts. I'm Matthew Viles, and this work was done in collaboration with Njati Jianjamgos and Richard Bowden. Disentanglement is a relevant and ongoing goal for the field of machine learning, which is important for a range of tasks including generalizability, causality, attribute transfer, and many others. The goal of VDSM is to achieve disentanglement between the identity and the motion aspects of objects in video sequences. Existing methods seek this disentanglement using generative adversarial networks, which can be tricky to train, explicit supervision for the individual factors, which can be expensive to attain, and domain-specific inductive biases such as physical laws, which can be restrictive in their generality. VDSM should therefore ideally achieve disentanglement without supervision, without adversarial techniques, and without domain-specific inductive bias. Unfortunately, it has been shown that unsupervised disentanglement is actually impossible without the use of inductive bias. One general type of bias that's applicable to video data holds that motion represents frame-to-frame changes in pose, which therefore varies, whilst identity remains approximately static. This is the top-level diagram for VDSM. The average identity across a set of frames is encoded and used to drive a mixture of experts decoder. The decoder therefore specializes in reconstructing the identity information from latent variable Sn. Meanwhile, the poses for each frame are encoded and fed to a probabilistic sequence-to-sequence network, which summarizes the motion being performed in latent variable Dn. This summary is then decoded into latent variables representing the frame-to-frame pose Znt. Finally, the poses are combined with the ID information to form the total input to the decoder, which is tasked with reconstructing the original frames. VDSM is generative and can be broken down into its generative and inference models. In generation mode, one can begin by sampling a motion Dn and an initial pose Zn1. Dn is used to drive a transition network which determines how this pose evolves over time. An ID is sampled from Sn, and the information is combined to produce video frames. Note that the grey shaded area represents the components which are trained in training stage 1. More on this later. This is the inference model. Frames are used to infer the average latent ID over a sequence, Sn. Frame-by-frame hidden vectors are used as the input to a probabilistic sequence-to-sequence network which summarizes the latent motion Dn, which in turn is used to infer the latent poses Znt. The two stages of training are as follows. The first stage only updates the encoder and the mixture of experts decoder to do the best that they can at deriving the average appearance over a sequence. The first stage therefore achieves a separation of identity or slow-changing information from everything else. The second stage builds off the first. Now that identity was successfully learned in the first stage, the relevant encoder and decoder weights are frozen, although some weights relating to variational parameters are still allowed to be updated to ensure a valid elbow, which we'll discuss next. In this second stage, the network can therefore focus on modeling the aspects of the video that change, notably the pose. The objective function is variational and constitutes a lower bound on the model evidence. In other words, it's a variational elbow. The first term is the conditional likelihood. The second represents the KL divergence between the motion Dn conditioned on the input frames and the prior for motion. The third term represents the divergence between the conditional identity Sn and the prior for the identity. And the fourth term represents the divergence between the first pose Zn1 conditioned on the input frames and the motion Dn and the prior for the first pose, as well as the sum of recurrent divergences between the conditional pose at each time step Znt and a conditional dynamic prior for each time step which itself depends on the pose at the previous time step and on the motion Dn. These results demonstrate VDSM's attribute transfer. The first column represents reconstructions of input sequences for the same identity. By keeping Dn static, we can swap latent identity vectors and thereby transfer the action to different individuals. This can of course be done the other way around by keeping the identity static and changing the motion vectors. Here is another sample for attribute transfers on the sprites dataset. The motions performed by the sprite in the first column are transferred onto sprites with different identities. The quantitative results show that a classifier trained on the representations encoded for ID achieve high ID accuracy but low motion or dynamics accuracy, as would be intended, and vice versa. For more results and more information about VDSM, please check out our paper. But in conclusion, VDSM enables disentanglement of slow-changing or constant identity features from motion and pose. It does so without the need for supervision, adversarial training, or domain-specific inductive bias, such as those relating to physical laws. Thanks for your time and for your interest.